this session, we recollect some main concepts of complex number system. The way it has been introduced is very interesting. Let us consider the equation x plus 2 is equal to 5. We know that there has been a unique solution in the set of natural numbers, that is x is equal to 3. X plus 2 is equal to 0, you consider this. To have a solution of this equation, we need negative integers. Thereby, set of negative integers is also established, or rather the set of natural numbers has been expanded up to the set of I of integers. Nextly, to have a solution of this equation, consider the equation 2x is equal to 3, we needed rational number system. Thereby, set of integers is now still extended to rational number system. And then to have a solution of this equation, say x square is equal to 3, irrational number system has been identified. Later on, to have a solution of an equation of this form or equation of this form, x squared plus 1 is equal to 0, we could find no real number which satisfies those equations, because if x squared plus 1 is equal to 0, then x squared is minus 1, and it is an easy matter to notice that there will be no real number at all whose square is negative. Therefore, the set of equations of the form x squared plus 2 is equal to 0, x squared plus 1 is equal to 0, etc., they are not supposed to have a solution in the set of real number system. To have solutions of equations of such sort, complex number system has been introduced to us. In the beginning of that, square root of minus 1 is introduced first, and it is named as I with the property that I square is equal to minus 1. I square is equal to minus 1. So that if you have x squared plus 1 is equal to 0, you can have this equation as x square is equal to minus 1. Therefore, x square is equal to I square. Therefore, x is equal to plus or minus I. It was made possible to have the solutions for such equations also. Justly because of this purpose, we could have developed a new number system, namely complex number system. Let us now go into the details of these complex numbers. Now, if x and y are any two real numbers, if x, y belong to R, then a number of the form x plus iy, which we generally use letters like z, z1, z2, z3, like this, like that, etc., to represent such numbers. Such a number x plus iy is called a complex number. Here I is equal to square root of minus 1. It is also termed as the imaginary square root of minus 1. Some students, or rather some lecturers and some others used to call it imaginary number. I is an imaginary number. Here z is equal to x plus y is a complex number where x and y are reals. Moreover, this x is called real part of z. That x is called real part of z, and this y is called, this y, the part y is called imaginary part of z. Imaginary part of z. Imaginary part of z. Real part of z is, of course, is denoted by the symbol REZ. Even though we write REZ, we read it as a real part of Z. Similarly, here, imaginary part of Z, we write like this. By keeping these things in view, Z is equal to real part of Z plus I into imaginary part of Z. Z is therefore equal to real part of Z plus I into imaginary part of Z. This is the basic definition of a complex number. Let us now go through some algebraic operations of these complex numbers now. Let us have two complex numbers of the form Z1 is equal to A1 plus IB1 and Z2 is equal to A2 plus IB2. Here A1, B1 are real numbers, A2, B2 are real numbers. As Z1 is a complex number, I is the imaginary square root of minus 1, that is square root of minus 1. Well, real part of Z1 is A1, imaginary part of Z1 is B1. Real part of Z2 is A2 and imaginary part of Z2 is B2. What happens if you add Z1 and Z2? You proceed in a usual way of addition of real numbers. A1 plus A2 plus IB1 plus IB2, that is I into B1 plus B2. Therefore, it is A1 plus A2 plus I into B1 plus B2. Even if you subtract Z1 minus Z2, what can it be? A1 minus A2 plus I into B1 minus B2. Like this, we usually use these operations. Again, Z1, Z2. What Z1, Z2 is? What Z1, Z2 is? You can think of it as usual multiplication. Multiply these two. A1, A2. A1 into IB2. I comes there. A2 into IB1. It also contains some I plus IB1 into IB2. I square B1 B2. What is I square? Minus 1. Therefore, this is A1 A2 minus B1 B2 plus I into A1 B2 plus A2 B1. This is the way in which we multiply two complex numbers. Z1 and Z2. Again, Z1 by Z2, it can also be defined as A1 plus IB1 by A2 plus IB2. A2 plus IB2. This can be defined as, if you multiply both numerator and denominator with the number A2 minus IB2, what is going to happen? This is A1 plus IB1 into A2 minus IB2 by A2 plus IB2 into A2 minus IB2. A2 minus IB2. Well, what is the fate of numerator? Just as a product of these two complex numbers, and the special interest will be of the case about the denominator. A2 plus IB2 into A2 minus IB2. What will it be? It looks like x plus y into x minus y in our usual real number system. What is x plus y into x minus y? X square minus y square. That is A2 square minus I square B2 square. You see, I square is minus 1. So minus I square is plus 1. Hence, the denominator would be A2 square plus I B2 square. Sorry, I'm very sorry. A2 square plus B2 square. A2 square plus B2 square. By looking at this Z1 by Z2, we will practice ourselves to have the reciprocal of any complex number. For example, 3 plus 4i. This is equal to 3 minus 4i by a square plus b square. 9 plus 16, 25. 1 by a plus ib. What can you have it? a minus ib by a square plus b square. Just like that. 1 by 3 minus 2i. If it is there, what can you have? 3 minus 2i. What will be the numerator? We generally multiply with 3 plus 2i. Therefore, 3 plus 2i by 9 plus 4, 13. 1 by 1 plus I. What is that? 1 minus I by 2. 1 minus I by a square plus b square is 1 by 2. Likewise, we recall the usage of usual arithmetic operations in general using complex number system. Next one. The geometric applications of complex numbers plays a vital role in the study of complex numbers. Yes, it is having a great importance. Let us start from the beginning about the so-called geometrical applications. You see, suppose z is equal to a plus ib is a complex number with s. We represent this complex number by the point a comma b in the general coordinate plane, which we call hereafter orthogonal plane. Orthogonal plane is nothing but the plane on which a complex number is going to be or can be represented as a point. This is AB. So, the real part of z is the x coordinate in that point, and the imaginary part of z is the y coordinate of that point. Right. Moreover, the complex number z is equal to a plus ib. If it takes the form of a point in the coordinate plane, it is generally considered synonymous with the vector OP bar. The vector OP bar. The vector OP bar. So, those concepts of vector algebra can also be used here also in terms of complex numbers. The complex number z is equal to a plus ib can also be represented as the vector OP bar, starting from O, OP bar. Well, this is the key point of representing a complex number z is equal to a plus ab on the orthogonal plane as a point AB, not only that, as the vector OP bar. Next one. Now, it is the time for us to know about the next heading, that is conjugate of a complex number. What is its purpose? How has it been brought into the fray? Let us see. Let z is equal to a plus ib. Z is equal to a plus ib. Observe its image in x-axis. It is just nothing but a comma minus b, isn't it? Now you produce the complex number a minus ib. Let me name it some z bar. Z bar. What is their sum? Z plus z bar is equal to 2a. Z plus z bar is equal to 2a. What is its product? Z bar. A plus ib into a minus ib. Come on. A square plus b square. A square plus b square. Here, it is essential to notice one thing. Both the sum and the product of these two complex numbers are real. It is real. 2a is a real number. A square plus b square is a real number. As such a complex number, z bar is supposed to be called the conjugate of the complex number. Z bar is the conjugate of the complex number. Therefore, what is the conjugate of 2 plus 3i? 2 minus 3i. What is the conjugate of a plus ib? A minus ib. What is the conjugate of I plus 1? What is the conjugate of I plus 1? Without getting any confusion, you write real number, real part first, imaginary part next. 1 plus I. What is the conjugate of 1 plus I? 1 minus I. That is minus I plus 1 is of course the conjugate of this. This is the way in which we mean the conjugate of a complex number. Moreover, as this is the image, if this makes an angle theta with x-axis, similarly is the angle it makes with the x-axis, of course, in the reverse direction. It does make theta in the positive direction and it makes in the negative direction. If this is say some 30 degrees, automatically this will be some minus 30 degrees. Now, we shall go into the details of these angles. What are they called and what are the significances? We shall know. The next heading, modulus of a complex number. At this moment, I would like to recall the actual concept involved in the word modulus. Suppose you are discussing with real numbers. Say some x is with you, a real number x is with you. What is meant by modulus of that real number x? It's just nothing but the distance from origin. In the real number system, what is the origin? 0. On x-axis, what is the distance of x from 0? Is nothing but mod x. What is modulus of 3? Imagine on the real line, 0, 3. Distance is 3. Mod 3 is 3. Mod minus 3. Distance of minus 3 from 0 is again 3. Now, let us turn our head towards a set of complex numbers. In complex numbers, suppose we have z is equal to a plus ib, a complex number before you. Z is equal to a plus ib, a complex number before you. Well, as we have just noticed, a complex number z can be taken as a point say AB in the origin plane. What is the distance of this point AB from origin? What is the distance of AP from origin? If you call this z, mod z is equal to mod OP bar is equal to square root of a square plus b square, isn't it? Whatever it might be the system, modulus of a number is nothing but the distance from origin. Here we are in the set of complex number system. If z is a complex number, mod z is the distance of that complex number when represented as a point in space, the distance from origin, root of a square plus b square. You might have recollected one more thing also. In three-dimensional geometry, if you have say a vector say ai bar plus bj bar plus ek bar, say r bar, then mod r bar is, what is mod r bar? Root of a square plus b square plus e square. Why should it be? That vector is synonymous with the point ABC, PABC in space. Of course, the vector OP bar is a bar plus bj bar plus ek bar, and mod OP bar is root of a square plus b square plus e square. There also we could have used the same sense and same sentence also. So thereby, modulus of a complex number we can mean as the distance of that complex number when represented as a point in the origin plane from origin. Therefore, mod z is equal to root of a square plus b square. Mod z is equal to root of a square plus b square. It means mod z square is equal to a square plus b square. Mod z square is equal to a square plus b square. Here, by knowing this modulus and conjugate, we can follow, we can recollect so many beautiful properties. What are those properties? Let z is equal to a plus ib be a complex number with us. Plus, what is z bar? What is z bar? A minus ib. What is z plus z bar? 2a is equal to 2 into real part of z. What is z plus z bar? 2 into real part of z. What is z minus z bar? A and AL we cancel. IB plus IB is 2IB. So it is nothing but 2I into B, that is 2I into imaginary part of Z. Imaginary part of Z. What is Z bar? What is Z bar? What is Z bar? Z bar, A plus IB into A minus IB. What can it be? It is just nothing but A square plus B square, and it again can be taken as mod Z square. What is Z bar? Mod Z square. Mod Z square. From this, we can always have, this implies Z by Z bar. What is Z by Z bar? What is Z by Z bar? Multiply it with both Z and Z on numerator and denominator. It is Z square by Z bar is equal to Z square by mod Z square. Z square by mod Z square. It is just nothing but Z by Z bar. Z by Z bar. The next one. Let us mix these using the properties of modulus of a complex number now. Modulus of a complex number. Mod Z, what is mod Z? Root of A square plus B square. What is mod Z bar? What is mod Z bar? Root of A square plus B square. Why? Because you observe this diagram. If this is Z, automatically this is Z bar. So this distance is equal to this distance, that is mod Z is equal to mod Z bar is equal to root of A square plus B square. Mod Z is equal to mod Z bar. Now let us go through some more properties. Z1 and Z2 are any two complex numbers. If Z1 and Z2 are any two complex numbers, Z1 plus Z2 whole bar is equal to Z1 bar plus Z2 bar. Even with minus sign, Z1 Z2 bar is equal to Z1 bar into Z2 bar. Z1 by Z2 bar is equal to Z1 bar by Z2 bar, provided Z2 is a non-zero complex number. Z2 is a non-zero complex number. Then with modulus, mod Z is equal to mod Z bar. Z bar is equal to mod Z square. And again, modulus of Z1 into Z2 is equal to mod Z1 into mod Z2. Mod Z1 by Z2 is equal to mod Z1 by mod Z2. Provided Z2 is a non-zero complex number, that is mod Z2 not equal to 0. Mod Z2 not equal to 0. Mod Z1 by Z2. And again, modulus of Z1 plus Z2, is it equal to mod Z plus mod Z2? No, it cannot be, need not be. This is less than or equal to mod Z1 plus mod Z2. Later on in future, we find the conditions as and when they become equal. Yes, we know. Another is modulus of mod Z1 minus mod Z2 is less than or equal to modulus of Z1 minus Z2 is less than or equal to mod Z1 plus mod Z2 also. Yes, therefore, corresponding to modulus of a complex number and conjugate of a complex number, we are supposed to recollect these important results which we generally use while studying with the properties of complex number system. Next one, we shall go through one more important concept regarding complex numbers. Now it is a case of special interest for us to deal with the important concept, namely mod amplitude form of a complex number. What is meant by that mod amplitude form? Basically, what is meant by amplitude? Let us now try to recollect that. Let Z is equal to x plus iy. be a complex number with us. Let z is equal to x plus iy be a complex number with us. We know that it can be represented as the point x comma y on the organ plane. Well, let OP be the vector corresponding to the complex number z is equal to x plus iy. We all know that modulus of OP bar is just nothing but root of x square plus y square is absolutely a positive real number, and let me represent that as small r. That is, small r is equal to mod OP bar is equal to mod z is equal to root of x square plus y square. Okay, let this vector OP makes an angle theta with x-axis in the positive direction. With x-axis in the positive direction. Then, as this is the point xy, this is x and this is y, and it is an easy matter, very easy matter to see that cos theta, what is cos theta from this diagram? X by r. Therefore, x is equal to r cos theta. Clearly, x is equal to r cos theta, and similarly y is equal to r sin theta. Use those two letters here. What is going to happen for the fate of z is nothing but r cos theta plus I into r sin theta. I into r sin theta. Yes, this is equal to, again it takes the form r into cos theta plus I sin theta. This form is of course called the mod amplitude form because the letter r involved in this representation is nothing but the modulus of z, and theta is the angle made by OP with a positive x-axis in the positive direction is called the amplitude of z. Amplitude of z. Okay, how to find that amplitude? To know r, it's very simple. R is just nothing but root of x square plus y square. What is theta? You see what y by x is? Y by x is equal to tan theta. Therefore, tan theta is equal to tan inverse y by x. And we can see many values for tan inverse y by x. How to denote, how to find theta perfectly? How to decide the value of theta? That is the case of importance in the present moment. Let us now take interest to know various methods, rather to know the accurate method of noting that theta. What is tan inverse y by x? How can it be? Right. This can be done in view of some examples. Moreover, according to the nature of x and y, whether they are positive or negative, we can notice the quadrant in which the point P lies. If P lies in the first quadrant, theta will be between 0 and pi by 2. If P lies in first quadrant, 0 less than theta less than pi by 2. Suppose P lies here. P lies in the second quadrant. Then what happens? This becomes theta. That is, P lies in the second quadrant, say like this. This will be theta. Then, what is the fate of theta? It lies between pi by 2 and 180. It is more than pi by 2 and less than 180. P belongs to second quadrant implies pi by 2 less than theta less than 180, that is pi. How to know whether P lies in first quadrant or second quadrant or third or fourth? Simply by noting the coordinates of P by looking at the complex number x plus iy. We have noticed that theta lies between 0 and pi by 2 or pi by 2 and pi, as and when the point P lies either in the first quadrant or second quadrant. What happens when it lies either in third quadrant or fourth quadrant? How to take the decision? Here is the right occasion to know one more word, that is the standard amplitude. Standard amplitude. What is meant by standard amplitude? The value of theta, numerically smallest value of theta, that is tan inverse y by x, according to the quadrant in which point P lies, is nothing but called the standard amplitude, or simply amplitude, or argument of jet. Argument of jet. It can be represented in the two ways, either AMP of jet or ARG of jet. We read it as argument of jet, we read it as amplitude of jet, which we mean in the same way, which can give us the same meaning, amplitude of jet and argument of jet. That is the standard amplitude. What is the standard amplitude? What is the difference between standard amplitude and general amplitude? It will be made clear by means of some numerical examples. Let us observe 4 complex numbers at a time. The first complex number is z is equal to 1 plus I. 1 plus I. If you note it on the organ plane, what is the point corresponding to the complex number? 1, 1. It is 1, 1. What is the amplitude? The point 1, 1 lies in the first quadrant. Clearly, what is R? Modulus of the complex number is nothing but root of a square plus x square plus y square, 1 plus 1, that is root 2. What is theta? Amplitude. How much? Tan inverse y by x. Tan inverse 1. Here, theta is able to be observed in the first quadrant. Tan inverse 1, theta in the first quadrant is nothing but 45 degrees. Therefore, theta is equal to pi by 4. Theta is equal to pi by 4. What happens to this case? Minus 1 plus y. This is, what is the point here? Minus 1 comma 1. Where does it lie? Minus 1 comma 1. It lies in the second quadrant. It lies in the second quadrant. Therefore, this is the amplitude. What is theta? We are interested in noting theta only. R is of course root in all the cases. Modulus is root 2. Theta, that is amplitude. Tan inverse minus 1. Tan inverse minus 1. Well, my dear, for this and for this also, y by x is minus 1, y by x is minus 1. Both are tan inverse minus 1 here and here also. Theta is equal to tan inverse minus 1. Tan inverse minus 1. Here the point lies in the second quadrant, whereas the point lies in the fourth quadrant here, 1 comma minus 1. Right. So here this is tan inverse of minus 1. Usually you take it to be tan inverse minus 1 is minus 45 as a rough estimate. But it is wrong here in this case, because this is of course minus 45. This angle cannot be said as minus 45. This is nothing but pi minus 45 or 135 or 3 pi by 4. Here it is minus 45. Why should you take minus 45? In the definition, the angle must be measured in the positive direction. This is not positive direction. If that is the case, you may have to say it with some 315 degrees. But you see, numerically smallest is supposed to be considered. Numerically smallest is minus 45. Therefore, theta is equal to minus 45 degrees or minus pi by 4 here. Therefore, if theta lies in if the point P lies in the fourth quadrant, then the amplitude lies between minus pi by 2 and 0. Here, in the case of third quadrant, what is the fate here? What is theta here? Tan inverse 1. Tan inverse y by x minus 1 by minus 1 is 1. Here is tan inverse 1. Here is also tan inverse 1. How to take the decision? Here it is pi by 4, the amplitude is pi by 4, whereas, what do you say about this? Third quadrant, -1 and -1. Either this angle or this angle. Numerically smallest is supposed to be considered to have the standard amplitude. If you have this, it is 225 degrees, 180 plus 245, 225 degrees, whereas this is -135 degrees. It is -135 degrees. The only consideration here to be made is the numerically smallest value. Therefore, here the amplitude theta lies between minus pi and minus pi by 2. Minus pi and minus pi by 2. It lies between. Therefore, in order to decide the amplitude, the standard amplitude, you have to know the quadrant in which the complex number, that is the point corresponding to the complex number, is placed. According to that quadrant only we fix the standard amplitude. Suppose standard amplitude is some alpha. Then the general amplitude is 2n pi plus alpha. In most of the cases, in most of the problems, we used to consider standard amplitude only. At very rare cases, in some very rare cases only, we are supposed to consider general amplitude. The general amplitude is 2n pi plus alpha, provided alpha is the standard amplitude or principal amplitude. Standard amplitude, principal amplitude, or simply amplitude, or argument. Then the general amplitude or general argument is 2n pi plus alpha. This is the way in which we consider the amplitudes, right? R, of course, here R is root of x square plus y square, root of x square plus y square, root of x square plus y square, rain root 2. Of course, but depending on the quadrant, rather the coordinates that can be given to the point P, which is going to be represented for the complex number Z, the quadrant will be decided, and by depending on the quadrant, the amplitude which we decide is dependent. Yes. This is the way to discuss about the standard amplitude and general amplitude. By looking at the previous discussion, we could have noticed that every complex number can be expressed in the form r into cos theta plus I sin theta. If z is equal to x plus I, y is a complex number, then z is equal to r into cos theta plus I sin theta. R into cos theta plus I sin theta, where r is equal to root of x square plus y square. No doubt it is the positive square root of x square plus y square, and theta is equal to tan inverse of y by x. Of course, this value depends on the quadrant in which z lies. That's very important. You see, for both 1 plus I and -1 minus I, we could have got same tan inverse y by x, that is tan inverse 1. But the proper decision is to be taken by noticing that the quadrant in which the point corresponding to the complex number z lies is known. According to that only, we are supposed to decide. This is, well, the next thing we shall discuss with some standard mod amplitude forms for some standard complex numbers. For example, you see the complex number 0, that is 0 plus I0. How can you say the amplitude for that? 0 is the complex number. What is its modulus? 0. 0 into, if you write whatever you like, it is 0. It is needless to write the mod amplitude form for 0. Well, then next 1. 1 means 1 plus I0. 1 plus I0 means 1, 0. It is a point on x-axis. It can be taken as cos 0 plus I sin 0. Why? 1, 0 is a point on x-axis. point on x-axis means it makes 0 with x-axis itself. Amplitude is 0. Next, minus 1. Minus 1 means here it lies. What is the angle? 180. So it is cos pi plus I sin pi. I sin pi. I. What is I? Actually, I is nothing but 0 plus 1i. Hence, the point corresponding to I is 0, 1. So, this is the complex number. What is the amplitude here? Z. What is the complex amplitude? Y-axis makes 90 degrees with x-axis. Hence, it is pi by 2. It can be taken as cos pi by 2 plus I sin pi by 2. And again, minus I. How can you say? Minus I. What is the point corresponding to the complex number minus I? Minus I is 0 minus 1 into I. Hence, it lies on negative side of y-axis, 0 minus 1. What is the amplitude here? It is minus pi by 2. Hence, it can be taken as cos of minus pi by 2 plus I into sine of minus pi by 2. Likewise, we will be able to know the mod amplitude forms of some standard complex numbers. There are so many other standard complex numbers which we will come across very, very frequently. Let us now show some interest. Let us now throw the focus on such things now. The next topic to recall is let us first recall and recollect the concepts about cube roots of unity first. Later on we discuss with fourth roots of unity, fifth roots of unity, and in general nth roots of unity. How can they be obtained and discussed with? Let us see. First of all, cube roots of unity. What do you mean by the word cube root of unity? Consider the equation x cube is equal to 1. X cube is equal to 1. Then x cube minus 1 is equal to 0. With the usual algebraic transformation, it can be written as x minus 1 into x square plus x plus 1 is equal to 0. Here, two things will arise. X is equal to 1 or x square plus x plus 1 is equal to 0. That is, x is equal to 1 or x is equal to minus b plus or minus b square minus 4ac by 2a, that is minus 1 plus or minus I root 3 by 2. 1 minus 4 is minus 3. Minus 1 into 3, root minus 1 into root 3, that is I root 3. Minus 1 plus or minus I root 3 by 2. Therefore, what are the cube roots of unity? That is, what are the roots of this equation? Roots of the equation x cube is equal to 1 are termed as cube roots of unity. Roots of x power 4 is equal to 1. Fourth roots of unity. Roots of x power 6 is equal to 1 are called sixth roots of unity, and in general, roots of x power n is equal to 1 are nothing but called nth roots of unity. Now we are interested in dealing with cube roots of unity. What are the cube roots of unity here? X cube is equal to 1 implies x belongs to, come on, one answer is 1, another answer is minus 1 plus I root 3 by 2 and minus 1 minus I root 3 by 2. These are the cube roots of unity. Here, the special item that can be observed here is square this minus 1 plus I root 3 by 2 whole square. What happens? Minus 1 minus I root 3 by 2 becomes minus of something you can have. That is the miracle here in complex numbers. Square of this complex number is obtained as minus of some complex number. Right? What is that? Let me call this as some omega. Minus 1 plus I root 3 by 2, which is omega square. A plus b whole square. A square plus b square. 3i square minus 2ab. 2I root 3 by 2. What is 3i square? Minus 3. I square is minus 1. 3i square is minus 3. 1 minus 3 is minus 2. Minus 2 by 2, minus 1. Minus 2 by 2, minus 1. Minus I root 3 by 2. Therefore, if you name this omega, automatically that will be omega square. Automatically, if you take that as omega, this will be omega square. This will be omega square. So, by observing this concept, hereafter, we just use the letters 1 omega and omega square. This is equal to 1 omega omega square. Here, among these three cube roots of unity, one is a real cube root of unity. Omega and omega square are complex cube roots of unity. Well, what are the properties of this omega? Look here, what is omega into omega square? What are omega and omega square? Actually, they are nothing but the roots of this equation. Omega into omega square is product of the roots. What is that? C by A, there is 1 by 1, that is 1. Thereby, you will be getting omega cube is equal to 1. And again, what is the sum of the roots omega plus omega square here? Minus b by a. What is that? Minus 1. From this, 1 plus omega square is equal to 0. Those two results help us a lot in simplification of so many other problems, numerical problems. Moreover, as omega cube is equal to 1, you observe omega power 4. It is omega cube into omega. 1 into omega is omega. Moreover, omega power 3n. Whatever might be the value of n, what is omega power 3n? Is nothing but omega cube power n. 1 power n is 1. Suppose we have omega power 3n plus 1. This is nothing but omega power 3n into omega. Is nothing but omega. Like that, what is omega power 3n plus 2? Omega power 3n into omega square. What is omega power 3n? 1. So it is omega square. Omega square. So, in general, if at all there is, say, some omega power 405, you observe. What is the value of omega power 405? What is 405? Is it a multiple of 3, or it does leave a remainder 1 or 2 and divide by 3? It is a multiple of 3. 405 is a multiple of 3, and what does it mean? It can be written as omega power 3n. Hence the answer is 1. What is omega power 151? Is it a multiple of 3? No. 151. 1 plus 5 plus 1 is 7. It's not a multiple of 3. Well, what is the nearest to multiple of 3 for 151? Omega power 150 plus 1 you can write. What is omega power 150? 1. 150 is a multiple of 3 into omega power 1. So the answer is omega. Like that, we can simplify whatever integral power of omega is before you. Wait, one more thing. Just now we have discussed that omega power 3n is equal to 1. Omega power 3n plus 1 is equal to omega. Omega power 3n plus 2 is equal to omega square. Well, let us add these. What is going to happen? Omega power 3n plus omega power 3n plus 1 plus omega power 3n plus 2 is equal to 1 plus omega square is equal to 0. A beautiful concept here. What are 3n, 3n plus 1 and 3n plus 2? Are they not successive natural numbers? So if you consider the sum of 3 successive integral powers of omega, it will be 0. How? You consider any 3 successive natural numbers, say omega power 10, omega power 11, omega power 12. This is nothing but omega. This is nothing but omega square. This is nothing but 1. So the answer is 0. Just like that. Omega power 14 plus omega power 15 plus omega power 16. What is that? Are they successive integral powers? Yes, of course. No doubt the answer is 0. How? This is omega power 12 into omega square. omega square. This is 1. This is omega. Answer is 0. Such type of discussion is just not necessary at all. This one simple step offers us that knowledge. Why? Because any 3 successive integers can always be put in the form 3n, 3n plus 1 and 3n plus 2. You take any 3 successive integers, they can be put in the form 3n, 3n plus 1, 3n plus 2. For some integer n, undoubtedly the sum will be definitely 0. One more thing. Suppose you have, what is omega actually we have? Minus 1 plus I root 3 by 2. From this we have 2 omega is equal to minus 1 plus I root 3. 1 plus 2 omega is equal to I root 3. In a similar fashion, omega square is equal to minus 1 minus I root 3 by 2. 1 plus 2 omega square is equal to minus I root 3. 1 plus 2 omega is equal to I root 3. 1 plus 2 omega square is equal to minus I root 3. As and when they are required, we will be able to make use of them for a matter of simplification also. Right. So, in this discussion, what could we have noticed? Omega power 3n is 1. Omega power 3n plus 1 is omega. Omega power 3n plus 2 is omega square. That is, if omega power m is given, if m is a multiple of 3, omega power m is 1. If m leaves a remainder 1 when divided by 3, omega power m is omega. If m leaves a remainder 2 when divided by 3, then omega power m is omega square. And the sum of 3 consecutive integral parts of omega is always 0. Is always 0. Yes. Let us now look at some other 4th roots of unity and nth roots of unity in the next session.